Here are some examples of the types of questions you'll see in section 6.3. And before I go through them, I'll just go through a couple things with you. So to solve for energy conservation problems, okay, first you always want to calculate the total amount of mechanical energy. So this is the kinetic energy plus gravitational potential or spring potential to start with. So before anything happens to the object on the system, kind of get the overall mechanical energy. What is that amount? Okay, if a known amount of energy is lost through friction, subtract this value from the total at the start. If the known value is lost, and this is what we're trying to find, include a variable for this value in the equation. So you'd have like your mechanical minus your energy lost to friction. Okay. And then you want to calculate the total amount of mechanical energy after something occurs. So you kind of set it up. You want to equate two total energies. The energy before will equal the energy after. Remember, mechanical energy is conserved, okay, and then you can solve for the unknown. So you can kind of find out how much is lost due to friction or anything like that. So this first question here, we have a car with a mass of 1,250 kilograms. It's parked at the top of a 25.0 meter long driveway. The end of the driveway is where the car is parked, or the end of the driveway where the car is parked is 0.085 meters above the level of the street. Due to a mechanical malfunction, the car slips out of park, rolls down the driveway, and across the street. Friction can be neglected here, so we don't have to worry about that. How fast is the car rolling across the street? So again, going over kind of what I just talked about, we want to find out, like, at the start, before anything happens, this car is at the top of the driveway. Okay, at the top of the driveway, it only has potential energy. This will be the total before something, in this case rolling down the driveway, occurs. Okay, when the car reaches the level street, only the kinetic energy remains because it's no longer above anything. Okay, so basically we can start with our energy total, or mechanical energy. So EM is going to equal our EP at the start of our driveway here. Okay, and so now we have to find potential energy. We know that it is mass times gravity times height. So we can put our numbers in to find our potential energy. So our mass of our vehicle, 1,250 kilograms times 9.81 meters per second squared times, again, we just want the height, which is 0.850 meters. The length of the driveway doesn't matter. We just want to know how high it is above our reference point, in this case, the street. Okay, so we can find our potential energy is equal to 10,423 joules. Okay, so now all of that energy, okay, like this is our energy before, equals our mechanical energy. When the car is rolling across the street, basically all of our mechanical energy is turning into kinetic energy. So, which means our potential energy is turning into mechanical. So now we want to find EK equals 1/2 mv squared. So EK is equal to EP. So this number will go here. Okay, so we want to solve for V. So V is going to equal the square root of 2EK over M. Put our numbers in. 2 times 10,423 joules divided by 1,250 kilograms. And we get our total velocity, or sorry, total speed, 4.08 meters per second. Okay, so this one's a lot like what you've been doing, okay, because friction is neglected. Okay, if friction, if it says like it lost this much friction due to driveway, then you go like your mechanical minus your loss of friction equals EP, and then like, so then your kinetic, you'd have to subtract that friction amount to get that. So just be careful with that. So question 2, an arrow of a mass of 85 grams is fired straight upwards with an initial speed of 48 meters per second. If friction is neglected, how high does it go? Okay, so for this one again, okay, we're firing the arrow straight upwards with a speed. So basically we start with EK, and all of that EK is going to turn into EP. Okay, or I should put an arrow. The EK is turning into EP. So initially our EK is equal to our total mechanical energy because it has no potential. It's just moving, but it hasn't started moving up yet. Okay, and then our mechanical energy will then turn into our potential energy at the top. Okay, and that's how we know how high it goes. Okay, so we're going to equate the kinetic energy at the start to the gravitational energy at the highest point. Remember, at the highest point, the arrows will have no kinetic energy because they'll stop and then they'll start coming back down. Okay, so really what we can say is our kinetic energy initially equals our potential energy at the final. Okay, and so kinetic energy is equal to 1/2 mv squared, which is equal to mgh. Okay, so like there's two ways to solve this. You could solve for your kinetic energy, then make it equal to this and rearrange and solve for height. You can do it all in one step. Totally up to you how you want to do it. Okay, if we do it in one step, then we don't need this mass, which is sometimes handy because like you aren't always given a mass. So if you aren't given a mass, you have to do it this way. If you're given a mass, you can do it in 2 steps. Okay, and so if we're finding for the height, we're going to divide both sides by mg. And so basically we're canceling that out. So we get, okay, v squared over 2g is equal to h. Okay, because these cancel here too. Okay, so now we just put our numbers in. So v squared, 48 meters per second. Make sure it's always in meters per second, not in kilometers per hour or anything else. Okay, times 2, 9.81 meters per second squared. Okay, and so our height in meters is equal to 117 meters. Okay, so now continue with that. So it says here that the arrow in the previous question actually rises to a measured height of 76 meters. How much energy is lost through air resistance? So it's a type of frictional force. Okay, as the arrow rises, how fast should the arrow be traveling after it falls back down to ground level? Okay, so for this one, basically we want to like our EK. So again, we write down like initially what's happening. So our EK minus our change in energy due to friction is equal to our EP. So we can put those numbers in. So our EK, so it's still 1/2 mv squared. We'll just put our numbers in here. So we want to convert our mass to kilograms, 0.0850 kilograms. Okay, times our speed, 48.0 meters per second squared, minus our energy due to air resistance in this case, is equal to mgh, so 0.0850 kilograms times 9.81 meters per second squared times our height, we said is 76.0 meters. We're in another room. Okay, so now that we have this, we can find out by like solve for this number, and then you want to find this sort of change in energy due to friction is equal to 35.4 joules. So that's how much energy we're losing due to air resistance as it's shot up. Okay, to find the speed on its way back down, we have to note that the arrow will lose an additional 35.4 joules, okay, as it falls back down to the ground. So it will use the highest point to start with. So our EP initially will be from that highest point, the 76 meters. Okay, but now it's going to lose that energy due to air resistance as it comes back down. We're assuming that the same amount of air resistance will act on it as it goes down as acted on it as it went up. Okay, and then that's going to equal our final EK. Okay, so we can now put our numbers in. So we know our EP is equal to, well, and like if you already have the number here, so but we'll just, sorry, 0.850 kilograms times 9.81 times 76.0 meters minus, we have this number, so 35.4 joules. I rounded it, but you should use the whole number in this case. That's going to equal 1/2 times our mass, 0.0850 kilograms times V squared. So now we're going to solve for all of this, rearrange for V. Okay. I'm not going to well, I guess I can show you all the work. Okay, I'll just solve. So we have 63.37 joules minus the 35 we lost there is equal to 1/2 mv squared. Okay, we'll solve for those. So we get our total joules, this minus this. Again, I use the total numbers for these, not the rounded ones. Okay, and that gives us 1/2 mv squared over here. So now to rearrange, okay, we'll times both sides by 2. That'll cancel with that. So times this by 2. Okay, and then we're going to divide both sides by the 0.0850 kilograms. That cancels there, 0.0850. Okay, and then we want to square root both sides to get rid of this squared. So basically we'll get V is equal to the square root of 2 times our energy change, or like, so our total mechanical energy initial, minus or divided by our weight, or sorry, our mass, and we should get 25.3 meters per second. Okay, is our final answer. Okay, and so if we didn't worry about air resistance, so like when we first started in this like chapter 1 and stuff, we never worried about air resistance. So we did some of these problems where it's like you shoot an arrow up and then it comes down. Okay, remember your VF would always match your VI. Okay, but now we're accounting for air resistance, and so it's a little more work because we have to account for the energy lost due to air resistance. Okay, if you have any more questions, if you want me to do more examples, I'll do examples straight out of your assignment if you want me to. Okay, or just feel free to email me and see if you're doing it right. I can give you the right answers. Okay, just let me know how I can help you.